Solid and Fluids Separations by Greg, Lee, and Marcus. An electrostatic precipitator is a device used in solid-gas separations. It operates under the principle of electric fields. It charges solid particles in a gas stream in an area of high ionization called a corona. The charged particles will then be attracted to the metal collection plates where they will build up and form a solid sheet. The solid sheet needs to be collected at frequent intervals to avoid buildups. This is done through a process called wrapping. The wrapping process is a shaking of the collection plates to cause the solid sheet to fall to collection hoppers below where they can be removed from the system. The shaking of the plates can cause some of the particles to re-enter the gas flow stream in a process called re-entrainment. These particles will have to be re-ionized and recollected. This can lead to a reduction in efficiency. Another reduction in efficiency comes from sneakage, where a small portion of the gas flow can avoid the corona and thus collection. ESPs often use several segments to increase the area for collection and to reduce the effects of re-entrainment. Depending on the application, different types of ESPs are preferred. A plate wire ESP is the most common type. It has two parallel collection plates with a wire hanging in between them to produce the corona. Plate wire ESPs are great for high flow rates, but require sneakage, causing some particles to inevitably escape treatment. A flat plate ESP is similar to a plate wire, with the electrodes covered by a flat plate. This increases the effect of the electric field, but requires more corona-generating electrodes. It is commonly used for particles with high electric resistivities. Tubular ESPs are very similar to plate wires. However, instead of parallel collection plates, it is surrounded by collection plates on all sides. This could be rectangular, hexagonal, or cylindrical. Tubular ESPs have no sneakage because they are cleaned with water and do not have a sneakage area caused by hoppers. Wet ESPs could be any type already discussed that use water instead of wrapping to collect particles. This leads to more efficiency due to decreases in re-entrainment. However, it costs more for recovery or to dispose of the solids. Two-stage ESPs separate particle ionization and particle collection steps. This usually requires a preconditioning of the gas and requires low gas flow rates. The data on this slide was given from the EPA. The wet ESP costs do not account for the solid liquid waste generated. This waste would need to be disposed of, and it is more expensive than dealing with pure solids. Scrubbers are an air pollution control device that removes solid particles from gas waste. Scrubbers use a scrubbing liquid, usually water, which captures solid particles, cleaning the gas. The way scrubbing fluid interacts with the gas depends on the type of scrubber used. A spray tower sprays the scrubbing fluid directly into the gas flow stream. A dynamic scrubber is similar to a spray tower and uses a power-driven rotor to force the scrubbing fluid into small droplets. Tray towers have a gas flowing up with the scrubbing fluid on trays dripping down. A Venturi scrubber injects the gas and liquid simultaneously and accelerates them briefly, which increases gas-liquid interactions. An orifice scrubber has a gas flow over a stagnant pool of scrubbing fluid. A pack tower is similar to a spray tower with additional packing material. This packing material is using an adsorbent material that can capture toxic or harmful gases. A condensation scrubber uses water vapor to interact with solid particles, which then forms water droplets which can be removed from the gas flow with a mist eliminator. A charged scrubber applies a charge to the scrubbing fluid, the solid particles, or both to increase particle interactions.
And next is spray tower. Spray tower consists of cylindrical vessel and some nozzles, which is used to make heat and mass transfer between gas and liquid. Spray tower are low energy scrubbers, so they are always used for air pollution control. Gas phase used for spray tower is continuous gas phase, and it contains some deeper solid particles, and usually enter the tower at the bottom, and leave from the top. Liquid phase is sprayed downward through the nozzle into the vessel. The liquid phase must be larger enough so they cannot be carried out of the tower by the outlet gas flow. So the nozzle would produce droplets with a diameter of 500 to 1000 micrometers. The gas velocity also should be kept at the low level. And next is the cost range for the spray tower under typical operating conditions. If the MRO is 6%, the capital cost can be calculated, and the result is shown below. And cost can be higher than the range if some application required expensive material or treatment method.
The distinctive feature of a Venturi scrubber is its throat. Similar to the throat in a rocket nozzle, the throat in a Venturi scrubber reduces the active area for fluid interactions before increasing it again. This serves to accelerate the fluid as it moves through the throat. This creates more turbulence in the fluid, which increases scrubbing fluid-solid particle interactions. More interactions leads to more solids being captured by the scrubbing fluid. After the throat, the fluid enters a cyclonic separator. In this section, the scrubbing fluid, now containing most of the solid particles, is driven to the walls of the vessel. As the gas spirals upward, the scrubbing fluid will lose its velocity and begin to settle at the bottom of the device. A mist eliminator at the top ensures the scrubbing fluid does not escape with the gas. The scrubbing fluid can easily exit the system out of the bottom to be disposed. The costs shown were given from the EPA in 2002 and converted to 2019 dollars using inflation rates.
Centrifuge is a device using centrifugal force to separate phases with different density. The basic operation principle is the sedimentation principle. It states that the particle having higher density than the solvent will ooze at the bottom of solution, and the lighter particle will flow on the top. There are three main types of the centrifuge, and their maximum velocity are shown below. Low-speed centrifuge is used for the normal sedimentation of heavy particles, and it doesn't contain temperature control. And high-speed centrifuge is always used for separation of biological sample due to the temperature control and higher speeds. Last one is the ultracentrifuge. The chamber must be maintained at the high vacuum and be refrigerated because intense heat is generated at high speeds. And next one is impactor, which is a simple device that contains air flowing around an impactor plate. Particles with enough inertia will slide across the airflow and hit the impactor surface. Impactors have been used to obtain ambient particles of different sizes, ranging from 0.5 to 30 micrometers in diameter. And there are two main types of impactor. The first one is a virtual impactor. It is to separate larger particles from smaller ones so that the both sides of particles can be sampled. The second is cascade impactor. It is a series of impactor plates connected, which is to collect the different size particles on the different plates.
The purpose of a settling tank is to exploit the differences in densities between a fluid and a solid. As you'll see, the differences in these densities cause a solid to settle to the bottom of the settling tank, allowing the clean fluid to flow at the top of the tank. These tanks have a large variety of applications, commonly used as part of the water treatment process. There are two main designs of a settling tank, rectangular and circular. Rectangular and circular settling tanks both follow the same ideas. There's an in-out flow for the contaminated feed, a path for contaminated feed fluid to flow, which allows the solid to settle before the fluid reaches the exit stream, and with the solid at the bottom of the tank. Normally there's a way to remove the sludge along the bottom. For a rectangular settling tank, the common way to do this is a conveyor belt. For a circular settling tank, the normal way is an arm rotating about the center of the tank, scraping the bottom. For separation to occur for a settling tank, the settling velocity of the solid particles must be large enough so that the particles reach the bottom of the settling tank before the exit, where they can leave with the exit stream. The height required for a particle to settle is equal to the vertical settling speed of the particle multiplied by the length of the settling zone divided by the flow rate of the stream. A critical settling speed, or the settling speed at which all the solid particles get collected, is defined as the height required for the particle to settle multiplied by the flow rate of the stream divided by the length of the settling zone. This is one of the most important factors in determining whether to use a settling tank. There are also factors that can be added to the feed to increase the settling velocity of the particles, such as a coagulant or flocculant. The settling velocity can be disturbed if there is turbulence in the flow of the stream. If there is assumption of no turbulence, the efficiency of the settling tank is simple and can be calculated by the settling speed divided by the critical settling speed. But with the more common assumption of turbulence around the sludge, the calculation of efficiency is derived to the settling speed divided by the sum of the settling speed and the critical settling speed. When sizing a settling tank, you would use these values to design the size. Walla Raj-Shaman created a cost analysis of a rectangular settling tank in 2009 with a flocculant feed of aluminum sulfate based on size. He created these equations using prior settling tanks that were built around the data published on them. The values from his equations were then moved up to present date using the CEPCI index. A hydrocyclone is a way to clean up a fluid contaminated with solid particles. The particles can't be too small, with a size of about 5 micrometers being the rule of thumb. Even with the larger particles such as sand, a hydrocyclone isn't perfect. That is why these machines are commonly used as a precursor to other separation techniques or as a simple rough cleaning method of fluids. It is also a very simple design with generally no moving parts. This design right here is the general hydroclone. As you can see, it is a stationary piece with an inlet feed being forced into rotating downward spirals. This causes lots of contact with the side of the walls, which gives lots of opportunities for the solid to hit the wall, causing it to lose lots of its inertia and fall at the exit on the bottom. Due to the pressure buildup at the bottom, the lighter fluid is forced out the top of the machine. Due to the simplicity of a hydroclone with no moving parts, it is very cheap capital cost wise. Although the lifespan can vary depending on use and feed, a hydrocyclone is very durable, so you don't have to replace it frequently. It is very safe as well, with the only hazards due to the equipment itself is the pressure buildup. It is also very easy to add onto almost any flow system. The drawbacks of this machine are the energy operating costs due to the pressure drop across the machine, since there's a lot of friction inside the machine, and a loss of momentum which requires energy to overcome. Also, as stated, the machine isn't perfect and doesn't work on extremely small solid particles.